Okay, good morning everyone. I'm Yatin, and today we will be discussing about efficient LLM decoding in this lecture series. Okay, so let's get started. So the first question is, why are we talking about efficient inference and not efficient training? What is the difference between the two, right, with respect to LLMs? So to answer that question, let's quickly recap, how it goes, how LLMs work, right? So for example, let's take a very simple sequence. The cat sat on a mat, and we are training the language model with this sequence, right? And at the time of training, we will do a forward pass through the LLM, right? So while we are doing the forward pass, at the end, we will get a probability distribution over all the tokens at every step, right? So this is token 1, this is token V, where V is the vocabulary size, and at every step, this is at step 0, we get a distribution over all the tokens, right? And this everything is done in parallel, right? We are not doing it step by step. At parallel, at every step we have a distribution. And what is this distribution supposed to mean? So well, when we are training, we train it in a way that we try to maximize the probability of the next token, right? So at the step 0, we would find the probability of the token which is the next token here, right? And we would try to maximize that. That is the learning objective in language model, right? So if you are given this we'll try to maximize the probability of cat. This is the token cat at step 1, right? And so on and so forth. Now, when we have trained this, right? When we have to do an inference, right? Let's say the input sequence is the cat sat, and we have to complete the sentence, right? So what we do is that we run a forward pass once with this input sequence, the cat sat. The language model will process this parallelly, the entire sequence, and will give us a distribution at every step, right? We have a distribution at step 0, we have a distribution at step 1, step 2, and step 3. Here we are mostly interested in the distribution at step 3 because that is what will tell us that is a distribution over the next token, right? So whatever is the maximum probability token in this distribution, we will pick that, right? So let's say it turns out to be on, so we will select this on. We get the next token, right? We fill it here, but then how do we proceed next, right? So in inference, we take this sequence again, the cat sat on, this is the new sequence. We pass it to the model, and again we will get a distribution. From the last step, we can again pick the token with the maximum probability, let's say and then again we fill whatever is the token with the maximum probability, we fill it here at the next step. We run the forward pass again, right, through the entire sequence, and we get the token with the next max probability, which is, let's say, mat, and so on and so forth, right? And here again we do a forward pass till we get end of sequence token, right? So we had to run forward pass 4 times to get 4 tokens. Now let us compare it with training. At the time of training, to process the same sequence, the cat sat on the mat, we ran the forward pass once and got the probability distribution over all the tokens simultaneously in parallel. Whereas at the time of inference, we had to run the forward pass once for every token. This is very expensive, and therefore we need efficient methods for running decoding, right? In our example, we ran forward pass 4 times to generate 4 tokens. This is not feasible at production scale, right? This is too much of latency and too much of time and resources wasted. Can we optimize it? Is there a way? Can we revisit the forward pass at the time of inference to optimize this, right? And to optimize this, let's focus on the attention layer, because that is the major bottleneck at the time of inference, right? So let us see. So this is to recap. This is one attention block, one block of the transformer, right? We have multi-headed attention, then layer normalization, then feed forward. This is the place where tokens are going to interact with each other. Everywhere else, it's going to be they are going to be processed independently, right? So these are the 4 token embeddings. For the cat and sat, they are color coded, right? Now we'll focus on this multi-headed attention block here. So the first thing that happens in the multi-headed attention or in attention is that we first have 3 matrices or weight matrices for query, key, and value, right? multiplying these embeddings with the respective matrices give us the query vector, key vector, and value vector. Note that each of these query vector is 4 cross d dimensional, where d is the hidden state dimension, right? And now I'm rearranging it here. So what happens when we are computing attention is that we have to compute. So when we have to compute the attention matrix, which essentially tells us how much a token depends on its previous tokens, right? And these are the normalized attention weights. And the output embedding for this token S, the start of the sequence, is going to be obtained by multiplying this attention's weight with the value of this itself, right? For the token the corresponding output embedding is going to be computed using these two attention weights. So what is this attention weight? This is the similarity of the token right, with the start of sequence. And how do we get that? We get that by using the query vector right, and multiplying it with the key of the start of the token, right? Okay, and so on and so forth. Now, and after this, after we have computed the attentions, we at the end of the network, we pass the embedding that we get at each step through a classifier, which gives us this probability distribution, right? So this is what happens in the first pass, and now and this gives us the next token p of next token on, right, for which the probability is maximum. Now, when we are doing the forward pass again with this additional token on, do we need to compute the entire softmax, or can we leverage certain things that we have already computed in the previous step, right? So we have already computed this attention matrix, at least partially, right? The output embeddings are also computed for the first 3 tokens. These keys and the values have also been computed earlier. We would not need the queries here because we don't need to compute their corresponding output embeddings now, right? The only thing that we need here is the query of on in terms of queries, right? So what we can do is that we can cache the already computed matrices that we have already computed in the previous step, right? So we create a cache for the keys. So this is the cache which contains the key values or key embeddings of each of the tokens from the previous step, right? And similarly, we cache the values v, right? And now to compute the output embedding here we need the attention weights here, right? And for that, what we do is that we compute the query vector for the last token that was generated in the last step, which is on. We take the key vector of the first token here, right, and compute the similarity score, and so on and so forth, right? Notice now that we are reading these key values from the cache, right? And now for on, we do not have its key embedding in the cache. We compute it and we cache it, right? And then this gives us the attention scores. So this will determine the output embedding for the token on, which will give us a distribution over the next tokens, right? So we can use the value vectors and the attention probabilities to compute the output embedding here. But then again, for the token which was generated at the last step on, we do not have the value embedding. We compute it, we cache it, and we use it to give us the output embedding for the token on. And once we have the output embedding here, again, we can pass it through. Once we are done with all the attention blocks, in the end we can pass it through the classifier and get a distribution over the next token. We pick the best token A, right? And in the last iteration, what we added to the KV cache was the embedding of token on, right? Key embedding of token on and value embedding of token V. We can easily discard the query embeddings because we don't need that, right? And we fill at step 5, and then we continue, growing the cache and, proceeding with the inference, right? So what have we done here is that we have divided the LLM inference into 2 parts, right? First is the prefill part, where the entire prompt, for example, here the prompt is computer science is, right? In this iteration, the entire prompt is processed parallelly, right? We create the KV cache, and then we decode, we get the next token. From iteration 2 onwards, we get one token at a time, right? And in the process, we keep on updating the KV cache, right? This is sequential from step 2 onwards. Each generated token is appended to the previous input, and the process is repeated until we get the stopping criteria, which is either the end of sequence token or the maximum tokens that we requested, right? Okay. So this is what summarizes our first optimization that we did, right? So what is the first optimization that we did? We created a KV cache which converted the entire inference into two parts: pre-filling and then sequential generation. And this reduced, where did it help us, right? We are growing KV cache, but we are computing less now. We are leveraging whatever we computed earlier, we are caching it, and we are using it again, right? So now let us look at the memory usage of KV cache. So this 2 here is for two matrices that we are storing, K and V. This precision is the precision, for example, are we storing the KV cache in FP32 or are we storing it in 16 bits, right? This is the precision. This is the number of attention layers, because for each layer you will have to maintain a KV cache. This is the hidden dimension, right? The dimension of each embedding. This is the sequence output sequence length, or the entire sequence that we are processing, right? For each token, we need to maintain a k and a v vector, right? So this is the sequence length, and this is the total batch size, number of sequences that we are processing in one batch, right? And let's take an example of a model, opt 13 billion. Here, let's say we are storing in FP16 precision. We have 2 bytes. We have 40 layers. Dimension is 5120, and this model, allows 2048 as the maximum sequence length. Let's say we are processing inputs of 2048 tokens, and let's say our batch size is 10. So this gives us a KV cache of 17 GB, right? For 10. For a batch size of 10, right? And the model size here is essentially 26 GB, right? So let's say we are processing it on a 40 GB A100, right, which has a GPU memory of 40 GB. Almost 65% is going to be used by the model parameters, right, 26 GBs, and roughly 30%, around 12 GB, is available for KV cache, right? So what is the expected throughput that we are going to get here is 8 batches of 2048 tokens, right? So this is again inefficient, right? I mean, can we do something better than this? Can we manage our KV cache in a better way? For example, here we have assumed that there are 2048 tokens in each sequence, but is that true? Are all input sequences of the same length, right? So how can we optimize it further? So for that, let's look at the memory management of KV cache, how the KV cache is managed in the GPU. Let us say there is a prompt, the cat sat, the same prompt that we were using earlier, and a prompt B, which is you only. Let's say with the 2 requests, in the first request we specify max tokens as 2048, and in the second one we have max tokens of 512. So now a typical standard KV cache manager, the way it allocates memory, it needs contiguous memory in the GPU, because most of the tensor operations, they require even matrix multiplication, right? They require keys and vectors to be in the contiguous memory, right? So here for the first prompt, we will have 2048 slots reserved. For the second prompt, we have 512 slots reserved, and depending upon the memory allocator that we are using, right, there will be some external fragmentation, right? They will not be allocated in the same space. There will be some space in between which will be kind of lost, some slots that will be lost, right? And now let's say when we are running the inference, we are at this iteration. This is the current iteration where we are. This token has already been generated here. The cat sat on, and here this is the first token that has been generated, right? So this KV cache is reserved for the input in both the places, these slots, right? This slot is, you know, for the tokens that have been generated till now. Then you can you know, let's say when you're managing it, you can assume that there are certain slots which will be used in the future. These are reserved for, you know, the future tokens that are gonna come in both the sequences. And beyond that, you know, there are a huge list of slots which go unused, right? So here this is internal fragmentation for a request, right? These are reserved. Why? Because we allocated the memory based on the max tokens, or you know, max tokens that the model can support, or the number of tokens in the request, right? Now, can we, you know, take some lessons from OS, which does a lot of memory management, and apply it here, right? So this scheme that we discussed, this chunk pre-allocation scheme, KV cache is stored in contiguous memory because most of the tensor operations, you know, require memory to be contiguous, and the chunks of memory are allocated statically. The idea here is that, you know, we don't want to move around the allocated memory again and again if it gets filled up, right? However, the actual input or the eventual tokens that we're going to generate could be much smaller than this, right? So this resulted in three types of fragmentation at any point in time, right? Some slots were reserved for the future tokens. Those will be used eventually, but at any point in time, you know, we are still reserving that. There is an internal fragmentation. This happens because we over allocate based on the max tokens which the model supports, or the max tokens based on the input request, right? Max tokens requested by the user, right? And then there is external fragmentation that happens because of the allocator, right? Because whenever it is allocating memory for a new request, there will be certain slots which we may lose in between, right? It may have its own algorithm for allocating these slots, right? So again, coming back to the previous example of 13 billion OPT model, if we have on a 40 GB NVIDIA, right, we discussed that the parameters are gonna occupy 26 GB, 65%. This is static. This will always be there because model parameters have to be loaded in the model and they have to remain in the GP always, right? And we get roughly 30% for the KV cache, which essentially means that with the existing allocation, you know, the way GPU memory is handled, we will max out with 8 batches, right? Now what we are going to discuss next, you know, is efficient management of this memory, right? And in particular, there is a system called vLLM which introduced paged attention, right? It's able to, you know, increase the batch size to up to 40. And what are they doing? They're simply managing the KV cache properly, right? Okay. And this results in you know, further increase in the throughput as well. We are able to process, if you are using the LLM server to process the request, you will be able to process roughly 3.2 requests per second, as opposed to 0.8 requests, you know, if you are doing it naively, if you are managing the memory naively, right? So let's look at, you know, how do they do it, and let's look at their motivation first. I mean, from where did they get the intuition, the idea? So the idea is very simple, and it is inspired by the virtual memory and paging, right, in the OS. So for example, in the, you know, the operating system, if it gets different, there are different processes which are running on the operating system, right? Each process requires its own memory, right? So process A, and then let's say there are two processes. In the physical memory, you know, it's not necessary that the memory will be allocated contiguous in contiguous chunks to each processes, right? So this is, let's say this is the physical memory, and we see that this page is for this page and this page 1 and 4 are for process 1. They are not, you know, contiguous. And then page 0 and page 2 are used by process B, right? If I draw an analogous here, this request A is the input prompt A that we have. It is analogous to process A. Request B is the input prompt B, or another input that we have. So this is the KV cache, which we will divide into blocks and manage it, right? So yeah, so this management of KV cache and vLLM is done, is inspired by virtual memory. We see the processes here as input prompts, right? Virtual memory is similar to something called logical KV blocks that we will see, right? So in logical KV blocks, for a given request, you know, the entire memory is going to be contiguous. All the pages are going to be contiguous, right? But in the so this is the logical KV block, and then we map physical memory to physical KV blocks. This is how, you know, GPU will store the memory, right? Here it will not be contiguous, and then we have a table of pages or a block table, right, to map virtual memory to the physical memory, right? Okay, so these are the analogous in the page retention or in vLLMs, right? So we will have these components there. Okay, so essentially what they are doing is that they are breaking the entire KV cache into blocks. Let's say each block is of size 4. Let's take that for example, right? And let's say there are 7 blocks here. So these are called physical KV blocks. This is where the memory will be, you know, the actual physical GPU memory will be allocated. This is the actual state of the physical memory. Now for each request, right, let's say we have first input that comes in. For each request, we will have a corresponding logical KV block. If there are 2 requests, we will have 2 logical KV blocks, but physical memory will be common, right? So there's one physical memory KV. Then we have a block table which will map logical KV blocks to physical KV blocks. So for example, let's say the prompt is, today we are learning about LLMs, and this is the input prompt. In the logical KV block, you know, the tokens are logical KV blocks are assigned to each token in a contiguous fashion. This is how the logical KV block will look like. The 0th block here is mapped to 7th physical block, right? So this sequence is exactly same here, right? And we keep a track of how many blocks are filled in a given, how many slots are filled in a given block, right? So all the 4 slots are filled here. Then the block 1 in the logical KV block is mapped to block 1 again in the physical KV block, and here only 3 slots are filled. We were tracking, right? Now let's say next completion is memory. The next token that we get is memory. We put that here in the logical KV block, right? We increment this number of filled to 4. We see that there is a slot available, right? We increase that to 4 and put the next token K and B, you know, keys and values embeddings for the token memory in this slot in the same block. Now this is filled, right? Now when the next token comes, let's say the next token is on. So today we are learning about LLMs and memory on. Now a new block from the physical KV is gonna get allocated on demand, right? Depending upon the condition of the physical KV, right? It's not necessary that it's gonna be contiguous. It's not necessary, right? We will add the corresponding entry in the, you know, block table, and number of filled tokens is 1. And when we get the next token demand in the actual in the logical block, it will be here contiguous to on. We look up in the block table, we see that number of filled tokens is 1, which is less. It's not, the block is not filled yet, is not completely filled. So we, you know, allocate this slot from the same block to the next token, right? And yeah, so that's how, you know, they view the entire KV cache. That's how they're managing the entire KV cache using paging, right? Now corresponding to the internal fragmentation in the previous, when we are doing it, when we are in the naive way of managing KV cache, there is an internal fragmentation here as well. But however, internal fragmentation is restricted to the is upper bounded by the block size. For example, here it cannot be more than 3, right? Okay. So now, and let's say we get another request, will have its own block table. We will allocate the corresponding memory in the physical KV block, right? And we will create the block table for this, and so that's how it will proceed. So this dynamic block mapping that we are doing, so what we did here was that it was allocating the memory on demand, right? So this dynamic block mapping, what does it enable us, right? In addition to avoiding allocating the entire chunk in one go, and reducing the internal fragmentation up to the block size, what else can it support, right? So it turns out that if we have, let's say, a single prompt and we need multiple completions for this, right? So have you ever seen this scenario where we have a single prompt and we would ask the model to create multiple completions for this? So beam search is one example, yes. And so when you use ChatGPT, have you ever seen that it shows you 2 completions simultaneously, and it asks you to pick the one which is the best, right? So I think you studied about alignment and reward models. So how are the reward models trained? Right, preferences of what over what? Exactly, right? So to create that data for human annotation, also we would create 2 outputs for the same input and ask the human annotators to pick the best, right? So this is a common scenario where for the same input we would require multiple outputs, right? And there is something called rejection sampling as well, where we do create multiple outputs and select the best based on, let's say, some reward function, right? Reward function could be even the sequence to which model itself assigns highest probability, right? I mean, it could be any reward function as otherwise. In fact, have you ever used Copilot, GitHub Copilot? Does it show 2 options, right? Right? So because there could be multiple code corrections, or there could be multiple ways of writing the code, the same function, right? And it may generate both, and the user may select the one which is which it prefers, right? So this is a very common scenario, right? And vLLMs, so for example, here we deliberately took this example because both the prompts are same, if you noticed, right? But then if vLLM is oblivion of it, if both the requests are coming from different users just as a matter of chance, then of course it will assign different KV blocks for both the requests. So but if it happens to come from the same user, and the request emanates from the same user, and the user wants to see multiple requests, can we do something better? Can we exploit the fact that there are common, there's a common prefix to both, right? So looks like this paging technique can do that as well. So let's look at an example. How does it do? So okay, so here this is the logical KV block. We'll definitely have logical KV block separately for the 2 requests, right? So this is the logical KV block for request A. This is the logical KV block for request B, right? Both contain the same tokens to begin with, right? Now in the physical KV blocks, they share the physical KV block. So only block 5 and block 7 in the physical KV are populated. Because we have a separate block table for both the requests, right? So this is the block table for request A, and this is the block table for request B. They are separate, right? We can right. So this is I think incorrect. So this should be, the first one is mapped to physical block 5, and the second one is mapped to 7. Yeah, so this is incorrect. So to begin with, they will have the same value, right? Now, when the generation happens, both sequences will generate a different token, right? Okay, so how do we manage for that? Which one will go in here, right? We have only one slot here. Okay? So any guesses how should it this be handled? Okay, randomly, fine. And how should we manage it? How should we, I mean, what happens to the other one then? Let's say this one, we get the output here first. Today we are learning about LLM, and let's say this comes out to be memory. Let's say randomly this is assigned memory. Then what will happen when this token gets generated? Let's say this is, today we are learning about LLMs and how. This is the next token which we need. So how will we do? We have to block this part here. Okay, and then how fine. Okay, so it's kind of similar to that, and in order to do it, what it needs to do is that it needs to maintain a reference count. KV cache needs to know how many requests are actually, you know, pointing to each block, right? So for both the blocks right now, reference count is 2, right? Let's say this token is memory that gets generated here, right? So first thing that we do is that we reduce, so we go here, we check that this particular block has a reference count of 2. That means someone else is also sharing it. I should leave it as it is, right? Because, you know, someone else is going to come later and will also require this. If I modify it here, that may create a problem, right? So I first reduce the reference count to 1. Exactly. Copy it on write. When I have to write, I first copy it to some other block, right? Let's say I allocate a new KV block 2, right? And fill the token, the KV for the token memory here, right? And now we will have to change the this thing also here, the page table, right? So now this second block is now mapping to physical block 2, right? And all the tokens are filled here, right? Now notice that this still has a reference count of 2, right? We're still, you know, even though we had to create a copy of this block 7, right? This is still shared by both, right? And now when the next token how is generated, and we have to assign a KV block, it goes here, it sees that the reference count is 1. That means I am the only one using it. It can easily assign the memory block here, right? For how, right? So we end up creating a copy, right? So how many times a copy will be created? Let's say we start with a big prompt which is occupying 3-4 blocks in the physical KV, right? So at max, you know, how many blocks will be copied over if there are 2 requests? Only one, right? The last one, right? The others will always be shared, right? So yeah, and then, you know, after this it will, because the reference count is now 1, this will never get touched anyway. This one will never get touched anyway, right? So this is 7. This will not get touched anyway, and everywhere else the reference count is 1, and the generation will continue as it is, right? So this is basically how KV blocks are shared in parallel sampling, right? Okay, so let's look at, you know, how did we improve the memory efficiency here, right? Remember earlier we had this allocation where for the first sequence, the cat sat, right, we reserved, this was 2048 map sequence that we reserved, right? And then there was another thing which was another example, we only, and for this we reserved 5 and 2 tokens, right? There was this external fragmentation, right? The cat sat, whatever the completion is gonna happen in the future, at this point we are reserving something for that as well here, these slots, these are the reserved slots. This was also some sort of a fragmentation that was happening, and then these is the biggest problem because they were never gonna get used because we over reserved. This was the internal fragmentation that happened, right? So out of these three, external fragmentation, reserved and internal fragmentation, how what are we able to reduce, right? So I mean, I've shown it here. Internal fragmentation is bounded by the block size. What about external fragmentation? Earlier, if a particular, again let me draw it again. Earlier, this was the part reserved for request 1, request A. This was reserved for request B. In between there were only 2 slots. Will they ever be used? They will never be used, right? So whereas here there is no such scenario. There is no such scenario where there are certain blocks which are left between two blocks. There are no slots which are left between 2 blocks as such, right? So there is no external fragmentation here, right? And how much are we reserving for the future tokens here? Are we reserving anything for the future tokens here? Yeah, so that is also bounded by the size of the block, right? So internal fragmentation is minimal. It only happens at the last block. It's upper bounded by the block size, and the number of wasted tokens per sequence is less than the block size, right? For a sequence, you never have anything allocated to it more than the block size. So it's always upper bounded by the block size, right? And notice that sequences are of the order of 100 or 200 or 1000 tokens, right? And relative to that, a block size, typical block size that is used is 16 or 32. I mean, I took 4 for an example, but with reference to that, it's kind of minimal. It's 1/10, right? And there is no external fragmentation here, right? So on an average, here the wasted space is typically less than 4% of the entire KV cache, whereas earlier, whatever potentially the KV utilization of KV cache could be, much more than that is wasted, right? So this is the advantage of managing the KV cache in this fashion, converting the KV cache into blocks and so on and so forth, right? Okay, so now the next question is that you remember that we allocated the memory in a contiguous slots. Why? It was done with the purpose, right? Because most of the tensor operations would require contiguous memories. So have you ever faced that in coding, that you create a slice of a tensor from 2 different places, and if you concatenate that, and if you try to do some operation in the forward pass, it complains. You have to do dot contiguous many a times, right? I mean, if you have gotten your hands dirty with PyTorch coding, you would know this. You would have faced this issue many times, right? So that's exactly the same thing, that it requires the 2 tensors. I mean, if you're taking 2 small matrices and concatenating them, if they are on different blocks in the KV in the GPU memory, you cannot run tensor operations on them, right? So you have to bring them together into contiguous space, which again is a costly operation, right? And here, what all do we need to do, right, to compute attention? What all do we need? So we have k and v values in the cache, right? When we get a new query, let's say q is the new query vector to the next token that we get, right? What do we need to do to get the output embedding of that token, right? What do we need to do to compute the attention? Let's say this is the query for that, right? So let's take our example, the cat sat on let's say here I am processing this token A, right? How do you compute the output embedding of this token? Let's say this q is the query of this token A, right? Q of A. What do you need to do? Let's say this is WQ. This is the output of WQ. So WQ times A gave us Q of A. This is the query embedding that we got. right? So what we first do is that we take the query, it attends on the, right, it attends on the previous tokens. We need, for that we need the keys, right? K of the, key of cat, k of sat, and k of on, right? We put that in a matrix and then multiply with the query to get, this is k transpose, right? So we yeah, right? So this is the key embedding of first, and this is the query embedding like this. This is the embedding dimension D, right? We multiply that and we get the attention scores, right? So A of Q with A of this query with respect to the, and so on and so forth, A of query with respect to on. These are the attention scores that we get. This requires a matrix multiplication, right? Q into K transpose. That's how you compute attention, right? And here we have only single query, so Q, right? But then these keys are not contiguous, are they? Because the way we have stored it in blocks, at max we can get only 4 or whatever, 16 or 32 keys in a contiguous memory. The blocks could be, you know, anywhere, right? So it may happen that let's say the block size is 2 and these two, the cat, right, is on block 1 in the physical memory, and let's say if this is the physical KV, let's say it may happen that the is here, cat is here, and sat is here, on is here. How do we do it now? Because these are not, this is not contiguous, this is not contiguous, right? Okay, so now how do we compute attention softmax? So that's what we need, right? Once we have these attention weights, we can compute that into probabilities by doing the softmax, right? So we'll have probabilities P of the to P of on, right? And then we again, once we have the probabilities, we again need the corresponding values, right? Because the output embedding is going to be summation of this Pi with V of I, where I is from whatever, the cat, sat, on, right? These are also not contiguous. So how do we do that? How do we compute softmax over fragmented memory, right? Okay. So any idea about this? So they define, you know, a new function which is paged attention, a new implementation of attention to do that exactly. And any guesses on, you know, how would they have done that? Very good. Yeah. So this is exactly, you know, at a conceptual level, this is exactly same as the higher level concept is same as flash attention. And what is that higher level concept? That higher level concept is essentially that you can decompose the attention, you know, into, you can compute attention over blocks and then recompute it, right? So it's I mean, it's very simple, right? So what you do is that, let's say in the same example, the cat sat on, right? What do I have to do? So the entire softmax, if I have to compute it over the entire sequence, it will be, you know, e to the power query into k1 plus e to the power query into k2 plus e to the power query into k4 divided by summation over all of these, right? Right? And if I compute it over only this, the cat, this numerator remains the same, right? And in fact, if I take a step further, right, I need to multiply it with the values v1 and v2 here, right, ultimately, and v4 here, right? Because numerator is the same, I can compute the numerator for each block. So for the cat part, I will compute the numerator, right, and I will store the sum separately. I can, right, when I'm what I need to, the denominator is going to be e to this summation e to the power q into ki. I goes from 1 to 4, right, in the entire thing. So I can again split that into two parts, e to the power q ki, I from 1 to 2, plus summation e to the power qi, I equal to 3 to 4, right, over the first part and over the second part, right? So what I can do is that for each block, I can compute its contribution in the numerator, right, and its contribution in the denominator, and then I can aggregate, right? So this is exactly what this says, that softmax over two blocks A1 and A2, right? A1 and A2 are the attention scores. attention scores can be computed independently, right? Attention score is Q into K transpose, an exponentiation of that, right? That can be computed separately for the two blocks, and this is what it is saying, that softmax over A1 and A2 is nothing but, it can be decomposed into the two, right? Alpha times. So what are these alphas and betas? What are these going to be, alphas and betas? Let's stick to this example. Right, so this exactly. So this alpha, for example, is going to be summation from I equal to 1 till 4 of K into Q, sorry, Q into K I transpose. This is divided by right, except that this should be in the denominator and the other sum should be in the numerator, right? Because this softmax over A1 already has a division with sum of the first two, right? You remultiply it with that and then divide by sum of all the four, right? So the same trick that we use in flash attention. And so how is vLLM and page attention results in efficient inference? Right, so it reduces memory fragmentation with paging. That is the first thing that we discussed. And the second thing is that, when you have to do parallel sampling, for example, in beam search or in general, right, you can reduce the memory usage by sharing of the KV blocks by multiple requests, right? So so this graph compares vLLM with standard Hugging Face dot generate, right? Have you ever used Hugging Face model and loaded that on a GPU and tried to use it to generate something, right? So when you do that naively, when you call a model dot generate with some input sequence, the cat sat, right, with respect to that you get 24x higher throughput in this case, right? And just like vLLM, there is another inference engine, which is text generation inference by PyTorch, right? Compared to that, also they get 3.5x higher throughput. I mean, when it was introduced, and later on, page attention and was also incorporated in TGI as well, TGI library as well, right? So at the system level, so we studied two concepts here, right? One was of paging, and the other was of paged attention, right? Together, so these guys have started a company that this originated from Stanford, and they created a product called vLLM, which is highly popular, and they are providing it as an end-to-end LLM serving engine. So what you can do is that you can pip install vLLM and then say start server and give the model name, right? It will start the server, give you a URL, and then you can send your request to that URL in parallel. Like different users can send requests in parallel, and even in fact in our research team we use it heavily. I mean, because there are for example, if I have to start a 405 billion model, right, it takes half an hour to just get loaded and started in multiple GPUs, right? So it's infeasible if everyone in the research team tries to upload, start their own model, right? So we use this very heavily. We use vLLM to have one hosting, right? And in the entire research team, we share the URLs, and the entire research team uses that in their research, right? So this entire serving that is there, it has three major components, right? There's a front end to it, then there is a distributed model executor, right? You need I mean, these days, if you are serving a big model, it will not fit on a single GPU, right? So you need multiple workers. These are the different GPUs, right? So this is a distributed model executor, and then there is a scheduler, which will schedule the different jobs, right? And there is a centralized engine that manages the block tables that we need, right? So essentially, this vLLM is mostly PyTorch code in PyTorch, and some CUDA code for implementation of page attention, and they are using Megatron for. So Megatron is a library which is used to split a big model into different on multiple GPUs. They're using that, and Ray is essentially a distributed parallel computing framework, which if they're essentially doing parallel computations here, right? So they need a parallel computation framework, distributed computing framework, right? So okay, so till now what have we covered? So remember, we started with the objective is efficient LLM inference. Why are we doing it? Why are we not talking about efficient LLM training? Because at the time of training, we know the entire sequence, and the entire sequence can be processed in parallel, right? Whereas when we are doing inference, we are generating one token at a time sequentially, right? And which makes it very slow, right? So first thing that we looked at, right, to make this fast is KV caching. This avoided multiple forward passes, right? This avoided redundant computation. Whatever we computed in the earlier steps, we cache them so that we can use them again, right? Then there also we saw that the memory utilization is not efficient. The GPU memory utilization is not efficient the way it is being done. And for that, we studied paged attention in vLLM, which introduced two concepts. One was the paging for efficient KV cache management, and the other was paged attention to compute attention using those GPU memories, right? But can we do something else? Can we, speed up the attention computation? So, for example, you pointed out flash attention, right? So, flash attention, the objective of flash attention and paged attention was completely different, right? Paged attention the objective was to do attention computation of a fragmented memory, whereas flash attention was introduced to speed up the attention computation, right? So can we leverage that? Can we speed up the computation itself, right? We have efficient management of the memory, but now can we speed up the operations, right? So of course, that's what we will study next, right? So how can we leverage flash attention for fast inference, right? So that's called flash decoding. Conceptually, it's very similar to flash attention. I will briefly recap flash attention, and then we will discuss flash decoding. So what have we handled? Here we avoided redundant computation, right? Redundant computation. Check. Right, this is efficient memory KV cache memory, or for GPU memory, right? For KV cache memory management, we did that. Check. Flash attention will cover speedy computations, right? Speedy computations. We'll cover that next, right? But still, the entire generation process is sequential, right? We are still generating one token at a time, right? So can we generate more than one token at a time? Can we generate 10 tokens at a time and then speed up? We get 10x speed up, right? If we get 10 tokens at a time, then that's 10x speed up, which matters a lot, especially when you're serving it in production, right? So that is the next thing that we will cover. That is called speculative decoding. Right, and within that there are different ways of generating multiple tokens at a time, and we'll discuss those, right? So that's it for today, and tomorrow we will cover first flash attention, and then we will cover speculative decoding and what are the different ways of generating multiple parallel completions with more than one token, right? So that's it for today. We'll continue tomorrow. Thank you.